This is Software Engineering Radio, the podcast for professional developers on the web at se-radio.net. SE Radio is brought to you by the IEEE Computer Society and by IEEE Software Magazine. Online at computer.org/software. DigitalOcean is the easiest cloud platform to deploy, manage, and scale applications of any size, removing infrastructure friction and providing predictability so developers and their teams can deploy faster and focus on building software that customers love. With thousands of in-depth tutorials and an active community, we provide the support you need. DigitalOcean stands out of the crowd due to its simplicity and high performance with no billing surprises. Try DigitalOcean for free by getting a $100 infrastructure credit at do.co/SERadio.
For Software Engineering Radio, I'm Medina Salinas. Today I have with me Pat Helland. Pat is a principal software architect at Salesforce working on a cloud-based multi-tenant database technology. Pat has been working on databases, transactions, and distributed systems since 1978. Previously, he worked on the big data plumbing for Bing at Microsoft. Pat co-authored the article titled "Too Big Not to Fail: Embrace Failure so it doesn't embrace you." Pat also writes a column for the ACM. Pat, welcome to the show.
Thank you. Thank you for having me.
Today we're going to be talking about web scale, failure, and recovery. I read your ACM column titled "Too Big Not to Fail: Embrace Failure so it doesn't embrace you." You begin talking about web scale computing and how this means running hundreds of thousands of servers. Can you give a bit more detail about what web scale computing is?
Well, thank you for having me. There's a lot of things that are happening with the web, as we all know, right? You have Google, you have Amazon, you have Salesforce, you have all of these companies doing work, and the demand that any of these websites sees gets larger and smaller over time. I mean, typically throughout the day, throughout the seasons, shopping season can make a big difference. And so you have to provision your data centers to be able to accept a lot of traffic and to be able to manage when it gets larger and smaller. And so you usually end up in a world where there are tens and hundreds of thousands of servers that are all working together to provide a function. And just the management of them, the life cycle of what happens to a server is in and of its own right a fascinating area.
Mm-hmm. You mentioned servers that you can be running tens of thousands of servers.
Sometimes hundreds of thousands.
Hundreds of thousands. So scale computing involves physical hardware and also software, for example, servers like you just mentioned, and we also have VMs and containers. Can you explain these three components? We can start with servers.
Sure. A server is a physical box. You can walk into a data center and kick a server. It's there. You can touch it. It takes electricity. A VM is a virtual machine, and that allows the software to pretend that the VM is its own server. But what's really interesting and cool about VM technology is you can run lots of things that look like physical servers on the same honest-to-gosh server, sharing those resources and using it to protect from one another as they use the same resources. Now, within that environment, you have components. Components are a really interesting technology that's emerged over the last 10, 15 years, which allows the easy deployment of software and they're lighter weight and they run inside of VMs or maybe in a physical machine, but usually inside of a VM. And they typically run as microservices where you can have a lot of computers running the same software, doing the same job in a fashion that adapts as the load comes and goes and adapts as things break.
The last one you're referring to are the containers, right?
The containers, yes.
Okay.
And they also make it easy with the microservice approach to containers to allowing you to roll out new software across a pool. You might have a few hundred of these running a particular job on your website, and then you can evolve the software. You always have to upgrade and change the software, and you might end up out of 200 servers, 150 are running the old stuff and 50 are running the new stuff as you're making changes.
I was reading about your career and I saw that you've spent the majority of your almost 40-year career working on transactions, also distributed systems. And as technology evolved, we now have transactional environments that can operate at a large scale. In your other ACM column titled Life Beyond Distributed Transactions, you talk about this thought experiment about almost infinite scaling. Can you explain what this thought experiment is about?
Well, it's not easy. There's some people who argue it's possible, but it's not easy to actually make transactions run across a very, very large set of servers, and certainly across trust environments where you don't know that the other computation involved over there is part of the same department or company. But if you're trying to run and make a bunch of changes, it's hard to make sure that they keep going when something fails. A transaction is, can I do the same thing and have work split into pieces across multiple servers and have all of it happen or none of it happen, so that the programmer doesn't have to think about partial results. I'm changing this, I'm changing that, but I don't have to worry about this happening without that happening. In many ways, though, as you spread this across servers, it becomes very similar to getting married on the telephone. People ask about atomicity in a transaction. Did it all happen or none of it happen? And to me, that's like, is the husband married, but the wife is not married? Or it turns out, the way we think of marriage, both of them are married or neither of them are married. And that's an atomic commitment to make it all happen together. But what if you're getting married on the telephone? What if you're on the phone and the person you want to marry is in another country, and they ask, will you take this person to be your wife or husband? And you say, I do. And then you get a dial tone.
Yeah.
There's a real dilemma here. Are you allowed to go on a date tonight? Can you do that? Yeah. And the answer is that atomic transaction depends upon being able to communicate. And so there's some good theory that's come out that's been proven, that you can't really know how to do that when there's failures in between and keep availability. And that's called the CAP conjecture: consistency, availability, and partition tolerance. Can you have all three? And it's been proven that if it's a classic notion of consistency, where I'm making changes and you're making changes, it can't quite happen so easily.
Mm-hmm.
Did that make sense?
Yes, that makes sense. You mentioned a couple of things: consistency, availability, and partition tolerance.
Yes.
I guess the one you're referring to in this phone call example is consistency, right? And also availability.
Well, and partition tolerance. Oh. When I got the dial tone, I got a partition.
Okay.
I can't communicate across the telephone when I got the dial tone. And so now I need to find out, how can this person I want to get married and I both have the same outcome? We're married or we're not married, but there's a dial tone in the middle. And so the answer is, the typical answer is you wait. You wait until you reconnect. And you find out, hey, what'd you say? Did you say I do? I said I do. Are we married? And that would be where the availability suffers because of the dial tone, until you can figure out how to get that answer that's consistent. If you want to go do your own thing without waiting for the reconnection of the telephone call, then you want to have availability and continue to move ahead, but you don't know the outcome yet. So you're giving up the consistency, the classic consistency of, I want to make a change and you want to make a change, and we both agree on that change.
Mm-hmm. This example that you just explained illustrates a failure happening. When we're talking about web scale and operating with servers, things can break and servers can fail.
They always break. They always break.
What are some of the reasons why a server in a data center can fail?
Well, first of all, servers are incredibly reliable. There's just a lot of them. And so some of them are broken. Disk drives are spinning things and they fail. They fail at a rate of, one will fail every 4 or 5 years kind of a thing. I mean, you look at the statistics and they will break out of nowhere. Power supplies can go out. Lots of things can happen so that the physical box that you purchased from the vendor no longer is functioning. And you have to realize, the way I think about servers in a data center is like a bag of nails on a construction site. They're all the same. Once in a while, one's bent and you throw it aside and you pick it up and you try to use them. And no one walks into a construction site loving and caring for each individual nail. You try to make sure you have enough nails by weight that you have extras so you can cope with things going wrong and some nails that get thrown away. These don't have a specific personality. Now, when you try to think about that as a complex computer that's participating in the cluster of the data center, you have to think about, how am I going to be okay if this one breaks? How am I going to continue to provide the web service that my website has signed up to do when a server will just plain break? If you have, a bunch of servers and you go like tens of thousands of servers and you go home for the weekend, pretty much what you do on Monday morning is figure out which ones to unplug and to send off and plug new ones back in, because there's going to be some broken in the morning.
That's a good analogy, because in the construction, if you get a broken nail, the whole construction is not shut down, right? Things keep going, and
that would
yeah,
they better, because you're going to have broken nails.
It's very similar to how we should react, in the sense that sure, one server went down, and
right. You bring extra nails. You don't get emotional about it. You don't hold a funeral for the nail. You just move on.
What is an example of this, of designing to expect failure without having human intervention and making sure things keep going?
Well, for example, the distributed systems, things that hold data. HDFS is a great example, right? Every piece of data is in a block, and every block is put on 3 different servers. And part of the system is constantly watching, can I still talk to all of the servers that have got my data? I may have 20,000 servers that are part of an HDFS cluster, and the name node is talking to them and making sure they're alive. If one of them is not alive, then it's got a list of where the copies of data are kept, right? Oh, this particular block is on these 3 servers, including the one that failed. That other particular block is on those other 3 servers, including the one that failed. And if one fails, then it says, oh my gosh, I got some work to do, and starts telling each of the servers that had a block that, was also on the server that failed, go put that block back to be in a 3rd place. So if you think about it, if a server has, I don't know, maybe 100,000 blocks on it, and it fails, the 2nd and 3rd copies of those 100,000 blocks are kept on different servers spread around the data center. And if you drop those server replicas from 3 to 2, wow, you got a problem. You don't have a crisis, but you have a problem. And so the problem gets solved by finding a place to put a 3rd copy for each and every one of them. And you want to spread it around. If you do this well, and HDFS does, then the act of going from where you've dropped down to 2 copies up to 3 takes less time than it would to actually copy all of the data out of the one server that died. The reason is because the 2nd and 3rd copies are in so many different servers who are going to talk to so many other different servers that in parallel, you can get back to coping with the loss of a server in much less time than it would take to actually read and write a single server. By getting back up to 3 replicas of that data, wow, you are now back to the point where you can take a licking and continue on. My joking way of thinking about this is it would be great to be able to walk into a data center with a baseball bat and whack a rack of servers, which drops the replicas for a bunch of data down to 2. And now the system says, whoa, and makes 3 replicas spread out across lots of different racks. And by the time you raise the baseball bat to hit another rack, everything was back to 3, so it can take another hit. Now, that's, of course, an exaggeration, but it's how to think about it. The failure is quickly repaired. The faster it's repaired, the more available the underlying data is. And that's the way we have to think about things in the data center.
So I see at least 2 design principles here. One is, first of all, have your data replicated, have more than 1 copy of it available, and also learn to recover quickly if that data is not available.
Correct. Availability is a function of how often failures occur, which is called mean time between failure, and how quickly you can recover from the failure, mean time to repair. And so if you can recover quickly, then your overall availability of the data goes way up. There's another point when dealing with data, which is that it's actually a lot easier to do these algorithms if the underlying data that you're keeping is not changing data. It's data you wrote once, and you're going to read it a bunch of times, maybe over years, and then you'll eventually maybe throw it away, but you're not going to actually change that data. You'll write other data rather than changing that data. And that's because what that means is as we go through this, oh, gee, I lost a replica, I'm going to go make some more. as you're going through that, you don't have to worry about the data being changed. That's a huge benefit.
One example I can think of is if somebody is looking up a book or a section in a book, that book has already been written. I know there are revisions that can make it change, but it's not the same as a bank account number.
Well, let's talk about those for just a second. The revision of the book is actually a different book in this approach. Okay, so you have the book for revision 1, and then you have the book revision 2, and maybe there's something that says, yeah, if you want revision 1, go look at this unique ID to go get the data. If you have revision 2, go look at that unique ID to get the data. But once you get to the revision, it's a unique thing. The other thing I wanted to say, you mentioned bank accounts. Bank accounts, it turns out, are handled as immutable data. If you have your May bank statement and you're looking at your May bank statement, to understand the status of what's gone on in the last year, you have to look through May and April and March and February and January and look back through them to interpret today. And furthermore, if you look at your May bank statement and you say, oh my gosh, there's a problem. You call up the bank and you say, there's a problem. And they say, oh yeah, you're correct, there's a problem. They don't issue a new May bank statement. They issue a change in the June bank statement that has not yet been sent to you. And so from the perspective of the bank, there's just a constant writing of stuff that once it is written is never going to be changed. And change happens in the new things that are yet to be written, and then they show up on your lap. And so that makes all of this mechanism work much easier in a distributed system. And that's why I wrote the paper called Immutability Changes Everything, is to get people's awareness raised about this, the advantages and the phenomena of how we're evolving to more and more data being treated as immutable data.
Mm-hmm. I want to talk about the hardware in the data centers a little bit more.
Sure.
Again, in that column that you wrote, Too Big Not to Fail, you talk about having to change hardware every 3 years, I think, and also the cost of this. So what I want to ask you is, why is it not cost effective to keep the hardware for too long in a data center?
Well, the hardware itself gets, the new hardware is more efficient than the old hardware. If you had a car from the 1960s and it was getting 10 miles to the gallon, and the gasoline was most of what you are spending to afford the usage of the car, most of it, right? That sometimes is true, sometimes is not. Then you might want to go down and get yourself a new car that gets, 40 miles to the gallon, because they're pretty good at it nowadays, or 35 miles to the gallon. And that ends up lowering your cost of ownership if the gasoline is a major portion of the expense. In data centers today, electricity and the physical, the physical building, but more electricity, are a much larger component over the lifetime of a server than the cost of a server. So if you can only fit so many racks of servers into your building, and you can only wire up so much electricity, it's much more the electricity than the physical space. Mm-hmm. And you can go get a computer now that gives you twice as much computation for the same electricity. When is it a good idea to spend some money to get that computer that gives you more computation? Now, there's no perfect answer here, but a ballpark that we can all kind of keep in mind is that the server is you're going to replace it about every 3 years. Now, some of the costs of replacing are decommissioning and then commissioning the new server. To decommission it, you have to get all the traffic off. You have to get all the data you want off. You have to unplug it. You frequently, in many cases, you want to take the physical disks and the physical SSDs and put them through a giant shredder, because you're very worried about the data being snooped on. And so if you actually turn it into a bunch of powdered iron dust by shredding it, then it's not so likely people are going to snoop on that data. And so that's a huge step that has to happen too. Now, when you commission the machine, you have to bring it in, you have to verify it, you have to make sure it's looking pretty good, you have to install the software, you have to install the data, then you can start sending traffic to it. Each of those things takes some time. So one of the concerns is, if I've only got 3 years between buying a server and using and throwing it away, how long does it take me to set it up and commission it? And how long do I actually have to spend decommissioning it? And those will consume part of your 3-year window that happens there. So all of this process is just a part of the routine of going through hardware in a data center. I'm very fond of saying that electronics and roast beef are worth less next year. And so it's kind of true. You buy that TV, oh, heck, I was over at a friend's neighbors across the street, and they had a beautiful plasma TV, and he's got it over the fireplace. And we were joking about the fact that if the TV gets messed up by the fireplace, it's probably not a big deal because the plasma, while it cost a lot a few years ago, there's something down at the store that you can buy that is going to do a better job for not much money. And so the same thing happens with servers in the data center.
Do you know the reason behind the 3-year window?
That's a ballpark. That's just the mathematics of when you see an expected reduction, the increase from Moore's law and the increase of what you're getting out of the server. It's been a rule of thumb, which gets revisited every time, as to how much more am I getting with the new server versus how much does it cost me to actually get rid of it and replace it and put it in. The figuring out when's the value of the new server such that it's worth taking out. There's no magic about 3 years, but it's kind of held that way for sort of 10 years, just that the new ones with Moore's law are going to give you enough to make it better to replace them. You also get what's called a bathtub curve, a bathtub failure curve. Imagine I'm making a plot over time where the x-axis is time and the y-axis is failures. How many components out of 10,000, how many servers out of 10,000 fail over, as time goes on? And so initially, when you plug in a brand new server, at first, some stuff fails and some percentage of them don't do so well. Then you use them for months and then it drops down and they're very, very reliable and not much breaks. And then as you start getting past 3-4 years into 5 years, then the failure rate starts going up. And the shape of this curve looks a lot like a bathtub. And that's why it's known as a bathtub curve of failures over time. And so you kind of want to test your way out of the initial failures that are happening. And you want to just retire the servers before they start getting really flaky later on in their lifetime.
So you mentioned this bathtub curve, and I just want to recap to make sure I understand. Is the bathtub curve because you commission a new server and at the beginning you see a lot of failures, so the number of failures is high, but then the server gets better and the failures are dropping.
They settle out.
But then at some point those failures are going to rise again.
Correct. Yes. And this is normal in many, many kinds of things, from cars to televisions to toasters. And that's why you see the 30-day warranty on a lot of things, is because you take it home, you try to use it, it works, and then all of a sudden within days it just doesn't work. And that's a common thing for manufactured stuff to fail pretty promptly in its lifetime. And then it gets good. And then as time goes on, it just kind of starts to wear out, different things in different ways. And as they wear out, they fail more often. And so, older cars, 20-year-old cars fail more rapidly than 1-year-old cars. But 1-month-old cars fail more rapidly than 1-year-old cars.
What I'm trying to understand is, when you first mentioned you see a lot of failures at the beginning, right? When you set it up, I imagine the setup wasn't correctly. There's probably, some misconfiguration.
It's just the funkiness of manufacturing sometimes.
Okay.
I mean, people, and you burn things in. The factory burns it in for a while before they deliver it. You get it into a data center, you stack it up in a rack, you burn it in before you put it into traffic, right? And try to eliminate those initial failures. But you can't end up burning it in so long that every server you put into production doesn't have some initial failure windows. But most of that beginning of the bathtub curve, you test away in the factory, or you test away before you actually deploy it in the data center. You stack it up, you're ready to deploy it, but you tested it. So, oh crap, this one's not working so well.
Yeah, that makes sense. And with the rise of cloud computing, all of these things of commissioning and decommissioning a server, they're handled by the cloud provider, right? For example, Amazon, Google.
Correct. Amazon, Google, Microsoft, all of those folks will. That's just part of the niceness of the cloud IaaS approach. Is you're buying a bunch of virtual machines, and the cloud provider themselves will take care of this aspect of things. Just like they worry about the electric bill, they worry about how did I get enough internet coming in and out. And it's a great offloading of a set of services for a fee to people who can do it more cost effectively at volume.
And with IaaS, you mean infrastructure as a service, right?
I do, infrastructure as a service.
Since we're talking about data centers and servers, let's talk a bit about maintaining and supporting this data center, particularly prior to DevOps. What did this look like back then?
Well, back in the day, and this is where you're thinking more of a classic IT shop, and you had hundreds of servers, and you had quite a few people who were managing them, and each of them they would know and love, and I jokingly say come in and pet in the morning, and the software would be installed by hand. People would worry about the how this particular server is doing, and take care of them with an awareness of the hardware and what its needs were. And that worked at small scale, tiny scale. As we started putting more and more servers, it didn't become, if you have 10 times as many servers, it wasn't practical to have 10 times as many, operators and support people. And so you had to figure out how this became more automated. And DevOps took us to a world where more of the stuff was automated, more of the routine stuff was automated. And so an individual operator could handle more servers than before when they were handling everyone with its own personality. To do the DevOps, though, you had to kind of reduce the awareness of the personality of each server. And you would say, oh, I want to do tens and hundreds of servers with the same stuff. And you all are running the same software, and we're going to install it in all the same software. As you get to web scale, and it gets to be hundreds of thousands of servers, you just can't do that, right? Everything has to be super automated. You have to have, basically no awareness of the personality of an individual server. As we mentioned earlier, it's got to be kind of like having a nail in a bag of nails. Mm-hmm. And it's doing a job and it's contributing, but it's not something you love and care for and are aware of what its quirks are.
Yeah. I was talking to someone and she told me that the servers even had names, like people would put names to.
Oh, yeah.
Yeah.
Oh gosh, yes. I could recount lots of names from my past of, and you'd be excited to get, a fourth one because you had three and you would come up with a name for the fourth one you got.
Yeah.
And that's where we have come from. But where we've come to is just turning that on its head, and you don't know the name of the server. It has a serial number that you just don't know.
Yeah, and she also said security was a lot of it. Is the room secure? Like the door is locked and things like that back then.
Well, that's because these things were not hooked up in sharing a network in the same way we are today. And people hadn't gotten into, breaking in across the network. And so security was definitely limited to the door and the lock on the door.
Yeah.
When I went to college, I had to drive down to the university to program. There were no PCs. And yes, I remember the 120 baud, that means 120 bits per second dial-up, but it wasn't practical to program across that. So you'd get up in the morning, you'd take a shower, and you'd drive down and program at the computer facility. And then you didn't worry about security across the network because there wasn't a darn network.
Mm-hmm.
And so this is a wonderful change. It's a great, new, and exciting thing. But like everything, we see echoes of the past that we came from. Every city has its streets laid out for the transportation of the day. And I've been to Old Jerusalem, and it was donkeys that were going between those buildings. And it's still very narrow, little windy, wet passages between the buildings. And similarly, as we've evolved our computing and our data centers, we carry a heritage from where we've been to, but we're inventing new things in a rapid way. And it's really fun and fascinating.
Mm-hmm. So with this, we started talking about ops, where there was a lot of manual work and you had to have a person assign particular machines to take care of. Then we moved to DevOps, where a lot of things were automated. You also talk about in your column this concept of no ops. What does this mean?
And that's not a common term. That is not a common term. But the notion is that so much of what had been done in operations staff, just with the manual operations and then the DevOps, becomes software managing the servers. And we're constantly seeing this trend that the behavior of the servers is all managed in a way where someone can detect, the software can detect a problem and can repair the problem. And so you end up with people only setting the broad goals and only dealing with super rare events that require attention, because almost everything is automatically handled. The thing that, to me, you just never want is pagers going off in the middle of the night on the weekend. You want to go home on Friday and everyone's doing what they're doing. And then on Monday morning, things are just there and there's some work to do, but nothing was a crisis because it was all things that went wrong were handled. And we're not all the way there, but we're getting there. And things continue to change year by year. And so, but to do that, to make software able to handle failures, and you have to have the behavior of the software you're running, the actual application and the infrastructure that's running has to have predictable behavior that the management software can handle. Imagine I have 50 servers that are handling a certain class of incoming request. For example, something from Amazon comes in, it's a recommendation. How many servers are there to handle the recommendation stuff that's coming in? And if the traffic goes up and these things are getting slower because there's too much work on them, automatically roll out more servers and say, you're going to do recommendations and we're going to send traffic to you, and have that just automatically handle it. And now the responsiveness of that service gets better because there's more to handle the load. That stuff should not require human intervention. And we're getting there as an industry. We're getting to the point where that stuff can be very nicely handled without people involved.
So no ops just means ops that are handled by software where the human is not involved.
Correct. And how far can we push that? And how much can we make that be the case? And this is an ongoing area of exploration by the industry. And it's getting better. It's really fun to watch.
DigitalOcean is the easiest cloud platform to deploy, manage, and scale applications of any size, removing infrastructure friction and providing predictability so developers and their teams can deploy faster and focus on building software that customers love. With thousands of in-depth tutorials and an active community, we provide the support you need. DigitalOcean stands out of the crowd due to its simplicity and high performance with no billing surprises. Try DigitalOcean for free by getting a $100 infrastructure credit at do.co/SERadio.
I want to talk now more about developing at scale and using stateless servers. First, I want to understand what operations at scale consist of. Can you give a few examples of operations at scale?
Well, just like I said a second ago about I want to take this service and it's going to get traffic. And if it's getting too slow because there's more traffic than there are servers, can that automatically be increased?
I see.
Well, that's one example of operations at scale and making that just work. And if you think about it, there's a lot of things that are implementing the web that behave that way. The front end for Google, things that are doing certain traffic for Amazon, stuff to support what we do at Salesforce. All of this stuff, the more traffic you have, the more you want to add servers to cope with the load. Now, being able to have work handed to any of a bunch of servers and have each of them able to do a fine job with that work, that's kind of where we get into the word stateless. And there is no crisp definition for stateless because state gets to be kind of funny. But on a whole, what it means is I can use more servers that didn't know about the last thing you did. It can handle the next thing you want to do. And so they can't really have an awareness of what you did before that they can't go learn from something else. If I have a shopping cart server that's behind me and I get some traffic and I can go ask the shopping cart, hey, what's in the shopping cart? And then get the answer and do more work for you, that's great. And that is considered stateless because the state is often the pool of shopping cart guys, right? And so what we tend to do with load balancing, if I have multiple requests from the same session, the same customer coming in, we tend to send them to the same server. And that's great because even though this server is stateless, it might remember some stuff from the previous time. It's like, oh, I went and looked up this customer's preferences, or I went and saw the things they were looking at, and I have some of it left over. So if the next request comes, I can do it faster. That's still stateless if that server can go and get the knowledge from some other part of the system to cope with the fact that they're not the one that got the previous request. Maybe it's a little slower because I didn't have it right at hand and I had to go get it, but it still gives the correct answer. So you can have stateless servers that have some caching to make the next repeated request from the same user faster, as long as they give the same correct behavior if you hit another server that has no cache and doesn't remember stuff from the past.
Yes, what you're saying is in the shopping cart application, if there's suddenly a failure, you get a new stateless server, and that is gonna ask someone else what was in the shopping cart and therefore be able to pick up where the user left off.
Correct.
I
Correct.
see.
For example, or the other preferences, or the you're looking for shoes, let's show you some shoes, that kind of thing, And there's stuff in that category where you want to cache stuff sometimes.
And that's the main reason why stateless servers are designed to fail, right? Because they don't need to.
Well, they will fail.
Yeah.
Every server will fail.
Yeah.
I mean, every server will fail on average, just ballpark, 1 out of every 5 years. Okay, so you could just do the math, right? Out of every 2,000 or so servers, you're gonna lose one every day, right? And so you just do the math of, let's take a year and call it 400 days because it's easier to do the math, and it's 5 years, so now that's 2,000 days. So every 2,000 servers, I'm going to come in the morning and one of them's broken, and that's the averages you'll see.
And what do we need to do to prepare for our stateless servers failing?
Well, have enough of them.
Okay.
And have an ability to bring more in.
Likely with automation, right?
Yeah, and so you get into this world where if I have a bunch of extra servers that are good for many different jobs in the data center, say there's 500 different jobs in the data center, and each of the servers can do any of those 500 jobs, and I've got some extras over here, and I'm losing 20 a day, and I have 150 extras over there, and I go home, and tomorrow I come in, and 20 of the extras have been automatically repositioned to do the jobs from the ones that failed, and then there's little red lights on the ones that are broken, and you have to unplug the ones that are broken and figure out what you're going to do to fix them or buy new ones.
Yes.
They're just there. It's just automatically, how can I make this stuff work? Now, as I mentioned, the stateless stuff is a little bit easier to deal with it failing, because you just kind of plug one in, you get the software on it, and it doesn't have to have a lot of knowledge. A stateful one, well, what you want is that state, just like we talked about with HDFS a few minutes ago. You want that state to be something where, oh, gee, I have an empty server that's going to work for this particular storage. Now I've got to put data in it. How can I and it's got a 10 terabytes worth of disk in it. Great. How can I get 10 terabytes of disk data off of the other storage servers, such that some of that data has gone down from 3 to 2 replicas, and I want to fill it up with some data that is spread around that data center. Because I've only got one server to fill with, say, 10 terabytes, it's going to take me a while. It'll take me a day-ish or so to actually get it up to full by the time I have to copy everything in across the network. Unlike the one that failed. When the one that failed, I don't have to put it through one network connection to refill it. That 10 terabytes can be spread out. So managing how the stateful data is kept and managing how the stateless computation is kept, those are important tricks for building large-scale data centers.
So in the case of the example of the shopping cart, when the stateless server is asking for the shopping cart information, they would be communicating to a stateful service. Is that correct?
Correct. And you may or may not want to keep shopping cart data across interactions, but you probably do, because shopping carts are allowed to be a little bit inaccurate, and the customer can still be happy. But if you hit a stateless server that doesn't know you and doesn't know how to find your shopping cart, well, it knows how to find it, but it doesn't have it already in cache. It'll say, golly, I don't have that. And it will go off to the shopping cart service and say, give me that shopping cart data. And now it'll get it and it'll do your work. Might take it an extra 10, 15 milliseconds to get that state from the shopping cart storage service, but it can get it and you won't notice too bad that it didn't have it in cache.
Part of preparing for a failure involves doing a lot of testing. When you're developing and testing, what is the reason why we use production data centers? Because I saw you mention this in your ACM column.
It's hard because you have a tension that goes on here. If you have dedicated testing data centers, frequently, not everywhere, but frequently, they end up kind of not having the best stuff. And so now the testing isn't working against the things that are out at the cutting edge with production. If you can actually share the production data center for test, then you end up usually getting a better representation of the production environment itself and a better ability to say, wow, I've really tested this thing. I know it's going to work in production because what it got was the same kind of behavior as production. But the challenge is you want to make darn sure that your developers and your testers can't, on purpose or on accident, cause a problem with production. Okay. So you could have, a nefarious developer who wants to go and spy on customer data. You can't let that happen. You have to isolate their access, and there have to be, ironclad ways to protect the customer's data from all employees and all other folks. You also can have a situation where the testing could consume so many resources that that production is impacted. And so you have to be able to isolate the test from the production resources in order to do that. Now, it is pretty nice. Production does go through an ebbing and a flowing, right? Where in the middle of the night, there's less traffic. At certain times of year, there's less traffic. And so being able to ramp up your test environment and consume data center capacity without impacting production is a very nice thing to be able to do.
So you can test in production, like you said, as long as you're isolating the customer data.
You want to isolate the customer data, and you want to protect the production performance so that you don't have too much traffic slowing down production.
That's why prior to testing in production, you can do it in a test environment, right? To get an idea of how the test performs.
Well, there's nothing wrong with having a test environment. It's great. The challenges sometimes are that the test environment doesn't have the best of the best, because frequently when you're sharing resources and things are scarce, you're hurrying to put things into production with the best of the best. Now, as the big broad data centers and the VM technology and sharing of infrastructure as a service is evolving, this is becoming less of an issue, because you can actually give production and test the best of the best and give them a lot of good stuff side by side. And we're seeing these very large shared cloud environments are able to isolate their customers. They do a phenomenal job of isolating their customers so that one doesn't impact the other.
Another component for embracing failure before it embraces you is the use of automated watchdogs. Can you explain what these are?
Well, you're watching the behavior of a pool of servers and making sure that the response time is good enough, making sure that things are actually behaving properly. And if I have 100 servers that are providing a particular job for the customers that are coming in across the web, you want to watch that the response time for them is acceptable. You want to watch that they're doing things that are acceptable and they're still alive. So out of those 100, you might want to actually walk through and talk, send a message to each of them saying, hey, you alive? How you doing? And then that's not perfect, but it can be pretty darn good in making sure that you're getting a system that, one of the 100 that are still doing a good job. And if it's not, then you want to remove it from service and you want to replace it with something that can now run the software and be up to snuff if the other one was sick. And so you end up with this, how can I test it to make sure the software is good and the hardware is good, and then pull it out of commission if it seems suspicious. You really do want to err on the side of removing something that seems inappropriate in its performance or its behavior, and so that you can only have stuff that seems like it's doing the right thing. And keeping an eye on that with automated watchdogs is a very valuable technology.
Does the watchdog involve humans in some cases?
Well, you don't want it to do it very often, or you're going to have to buy a lot of humans.
Yeah. Well, what I mean in the sense of, like you mentioned, the watchdog can detect something and figure out the recovery. But in some cases, do you want to, call somebody at 3 a.m.?
Usually, no. Not if it's 1 out of 100, for sure. And the other thing to realize is It takes some time to get your head around this. You don't want a sick server. You don't want to coddle it to make it healthy. Okay. You want to take it offline so the remaining ones are healthy. And then once it's offline, the question is, okay, can I remove all the data on it? Can I replace the software on it? And is the physical server still working okay? And the answer is usually yes, but sometimes no. And so you just don't want a sick server. If something is getting full of data, we weren't garbage collecting enough, and even rebooting it isn't good enough to make it better, then you want to take it offline. Having stuff that's sick only makes the complexity of the data center higher. And having a higher complexity means you have less predictability of what you're going to get.
Yes, that makes sense.
So it's kind of ruthless, but it is just a server.
Yeah, that's true. And we've been talking about developing at scale and what this consists of. Now I want to shift the conversation to data at scale because it's an area that you worked on a lot. And as we are scaling, we see the amount of data growing. How has this changed, for example, classical SQL databases? Have they changed?
Well, yeah. I mean, they've changed and they haven't. What I think has happened more is that people don't realize that you can't take SQL to the cutting edge of size that you can take other kinds of data. Immutable data, and by that I mean data that you write once, you read it a bunch of times, and you can eventually throw it away. That's cool. But you're not vibrantly changing it. That you can scale at enormous paces. It just can go like you wouldn't believe. But SQL is only kind of gradually getting larger in its ability to handle relational data that you're doing, SQL updates against and changing. Because I tend to think of all of this data as coming out of individual stars in the sky. And we have many, many stars in the galaxy and many, many galaxies out there, each of which is emitting changes to data. But the stuff in between is all stuff that you wrote once, you're going to read it many times, and it is what it was, and it was what it is. And that's a different attitude towards things. When you look at these ginormous big data centers and data sets that we have, they're data that you write once and you read it for a bunch of times and then you throw it away after a while. When you see a big, company like Google crawling the web, there's a lot of cool data, but you're not updating that like a SQL database. You're writing things out. You've got these immutable data sets. You use them and you do these incredible things to do searches against them, but it's not a classic updatable SQL data set. Not that I don't love SQL. I love SQL. I just think it's one piece of the pie of how do we build, and manage data. And when you talk about scale, it's almost always comes down to things that you write once and read many. Big data like Hadoop and MapReduce is always, I've got a very large data set. It's immutable. It never changes. I read it. I do a functional operation on it. I process that data. I produce an output data set that is immutable also. And I have ways of breaking that up to do parallelism to get the answer, but it is still an immutable data set in, functional transformation, immutable data set out. Most of our emerging computational models follow that same thing.
So would you say that one of the main limitations of SQL is the fact that it's relational data?
It's a limitation and a strength. Relational is phenomenal. It's brilliant. It allowed us to go amazing places, and we still are. But at the same time, in order to do the semantics of the set operations of relational data, you have to make everything look like it's still. And everything look like it's here. And so to do that, what we have to do is transactions to make it look still. And then it tends to run on a single server or a small set of servers that are close by. And so that's a paper I wrote called The Singular Success of SQL. And the idea is that it's a singularity. You're collapsing space and time in order to be able to do the set operations. That's brilliant, but that doesn't run at web scale. And so we haven't, as an industry, figured out how to connect those concepts that I use this here and I use that there. That's still something we're working on.
Another important thing when working at scale with data is that data can come from many different sources. What are the challenges of this data coming from different parts?
it's a joy. Data coming from different sources is just a phenomenally fascinating area. I equate it to how well do I understand some person I meet. And we all have differing backgrounds, differing understandings, differing ways of using words. My granddaughter is 17. She's awesome. She's a teenager. I understand about half of what she says, right? Because she's a teenager. And so this ability to understand data from different sources is very much the same thing. If you're at company A and you get data from company B, so many of the expectations and understandings and environmental concepts are just wedded to our different worlds, right? Our different expectations. I talk differently to people on my team at work than I talk to people in other teams at work, than I talk to someone at a computing conference talking about distributed systems, than I talk to the person who's helping me at a restaurant, and then I talk to my wife. They're all different interactions having to do with our common expectation. Data fits the same pattern. What the heck does that mean? How do I understand it? Now, one of the fascinating things to me about integration of data is that you got a metadata for your data. I got a metadata for my data. And when I interpret yours to be mine, some of the knowledge doesn't move through that interpretation. I call that a lossy transformation. And as I try to get everything into data sets that I can understand, I lose knowledge based upon where they're coming from and what's going on. Now, what people do frequently is they say, here's the canonical way of representing an employee or something, or a customer. But when you take somebody else's customer definition and bring it in, great. But that transformation lost some knowledge. Now, when I go from that standard canonical one into mine, I lost knowledge. And so that is what I call a double lossy transformation. Those are painful, but it's what we usually have to do because of the complexity of the system.
Yes, that's correct. And I wanted to follow up with the shape of how this data can come in. For example, what are some of the different formats that we might encounter when getting data from different sources?
Well, data is sometimes formatted to be understood internally, right? And when you have stuff in a relational system, it's designed and formatted to map the DDL. When you want to push something into the outside world, and I call that outside data in a paper I wrote called Data on the Inside versus Data on the Outside, you want to describe the metadata for it. And usually you're representing that where it's the data is meant to be read for common understanding. 13 years ago, XML was the style, right? Now it's JSON is the style. I view them as equivalent. JSON's a little easier to make the libraries for, but they kind of are the same thing. It's a semi-structured data where you can annotate with your own metadata. And so saying this is what I meant at the time I wrote it is super useful. Now, after that, there's the old Wild West of how do I describe what this means? And everybody and his brother has different definitions for what it means. And in my mind, the economics of understanding data at a distance, it's based upon economics. If you have an extremely large retailer that can tell the manufacturers, if you want to sell in my store, because I've got half of the United States buying out of my store, then you have to have this representation of the data. Guess what? The manufacturers are going to figure out how to fit it into that representation. And that's what I call the dog wagging the tail. And almost all data integration is related to which has got the most economic incentive to map to the other.
Yes. And how do you compensate for the lossy transformation?
You don't.
Okay.
I mean, you can work harder to make the lossiness less. It may or may not be worth it.
In what ways?
Well, you can try to have people in, teams study what did you mean by this, and I'm going to map it to that. But on a whole, you end up having software that gives it a good try, and it's good enough. It's on pretty much you have tools that do a pretty good job, and then the business need is met, and you don't choose to sit down and try to understand even more. If I have a product catalog and a bunch of suppliers are giving me descriptions of products, how do I know that emerald means the same as Kelly green, which means the same as forest green? Or is it a different thing? Or is chartreuse a different kind of green? And you end up with all of these descriptions of these products, and they're kind of a mess. And you end up sometimes you apply machine learning to it, where you end up seeing these patterns, and after a while you say, oh, I saw later on that meant the same as this, so I'm going to probably assume that means that. But this is there's no crisp and concrete answer to how you make metadata align.
I see.
Always going to be confusing. And that's kind of fun.
Before we finish, I want to talk about the alternative to SQL, which is called NoSQL. And I want to talk about this in the context of scaling. But can you first explain what the difference between NoSQL and SQL is?
Well, SQL is a relational system that when you bring everything together, and it can handle terabytes, tens of terabytes of data, when you bring it together, you can do phenomenal analysis and phenomenal combinations of the data in a way that are designed to let you vibrantly update it and still have meaning. And I continue to believe that this is an incredible thing that will move forward. But it turns out that doesn't work at the web scale to just say, well, it's all one big SQL database, because the pressure on making the changes happen and the pressure on bringing everything together is more than what works, given, well, frankly, speed of light and distributed systems, and nothing can happen that quickly to make it that good. So people have kind of built a bunch of systems which they create a key value store. I don't usually like the name NoSQL because it's less about NoSQL and more about we're storing stuff in a way which the key and the value are what we're focusing in on. And when you do that on a whole, you don't end up with many of the rich characteristics of how do I do queries and updates against SQL, but you get scale. And you get the ability to support a lot of people and a lot of data doing a lot of cool things. I view both of them as tools in the toolkit to make a solution. And they're neither right nor wrong, but you have to say, what's my business need? And how can I apply technology to meet what the business needs? And I mean, don't get me wrong, I think scalable key value is a phenomenal, interesting area, and a lot of products that are really, really cool for that. But kind of different. One does one thing, one does the other, and you give up this to get that, and that's okay, right? Just an area I think is under discussed in key value stores is that sometimes you want to have an answer which does not wait if things are breaking and things are broken or things are slow. And we see that you can actually give a fast answer to a key value store for a thing like a shopping cart or something by taking any of a set of recent responses. If I'm going to do a change, I don't necessarily stall behind a server. I'll keep writing. And one of the things I like to say is, do you want it right or do you want it right now? And some business needs want the faster answer more than they want the always last answer. And that's an interesting area of research for people.
I see. But what you were saying is there's NoSQL systems, or in other terms, the key value systems, they give an answer right now, so pretty quickly because they're fast and they scale, but it's not necessarily the right answer.
Not always. No. I'm saying that most NoSQL systems, most key value systems will always do their best to get you the last answer that was written to the key. But part of that deal, part of what happens there is that if one of the servers is in fact exhibiting a sickness and is not well, that may cause the system to go slow for tens of seconds or a minute and not give you the answer right away to give you the perfect answer. And they do what they're designed to do. And that for some uses is the right thing. For other uses, you would rather get a recent answer rather than wait a long time. Depends what the business wants and what the customer wants.
What's an example for a business and a use case where the key value one?
Well, if I'm reading out of a product catalog and I want to see an image of a watch that I want to buy, and the watch is being updated, the description of it is being updated, I'm not that excited about whether I get an older version or the latest version of the watch description. I don't even know. And I just want to not wait for the picture of the watch. I'm going to be frustrated if the system stalls for a minute while it's doing whatever it does. And it turns out, even in many cases for shopping carts, that users leave if it takes a long time to get an answer to what's in the shopping cart. They don't leave if the last change to the shopping cart isn't reflected in the shopping cart, and they'll just do the change again and it kind of settles out. And so on a rare case, you would prefer to actually give a quick answer, even if it is not necessarily the perfect answer. but it depends upon the business use and what the customer is doing and what's best suited to give the customer what they want.
Yes, and for something more precise, it would be SQL, for example, like a bank, right?
Well, yes, for banks, but that's not necessarily SQL. It could be, a key value store that is doing it. But there are these questions of, do I want to wait to get the perfect answer, or do I want to give a quick answer? And it's interesting when you start taking apart what people do and how things work. And I think this is an area of research that we're all going to be working on, is how do these distributed systems offer better behavior for people as time moves forward?
Well, Pat, thank you for taking the time to come on the show. It's been great talking with you about web scale and failure and recovery.
Thank you for the opportunity, and it's been great to meet you, and I really appreciate all that you do for this. This is a heck of an investment of your time, and I thank you for what you're doing for the community.
Thank you, Pat.
Thanks for listening to SE Radio, an educational program brought to you by IEEE Software Magazine. For more about the podcast, including other episodes, visit our website at se-radio.net. To provide feedback, you can comment on each episode on the website or reach us on LinkedIn, Facebook, Twitter, or through our Slack channel at seradio.slack.com. You can also email us at team@se-radio.net. This and all other episodes of SE Radio is licensed under Creative Commons License 2.5. Thanks for listening.